Right, now I'd like to move on to take a look at work and energy, subjects of chapters 6 and 7 in your textbook. And so a lot of times when we talk about work and energy, or somebody has a powerful personality that took a lot of work to complete, is very energetic person, those kinds of terms are somewhat synonymous in our normal English language, but they have very specific definitions in physics. And the reason why we look at these concepts is that it gives us another way to solve problems. And although we already have Newton's second law, F equals ma, to solve a wide variety of problems, oftentimes the work-energy principles can solve certain types of problems in a more efficient way. And so given that this is a tool, a mathematical tool that we can use to help us basically to add to our toolkit of ways that we can handle physical problems, we'll take a look at the concept of work. Now, we can think of just kind of really generally work as being forced through a distance. But it isn't quite that simple, because we are in effect looking at just that part of the force that goes in a particular distance. So if we define work by the symbol W, we can set that equal to F dot X, where this is a dot product between a force vector and a displacement vector. So here in this example, we have a force vector that is oriented at a certain angle to the horizontal. And so this dot product is the same thing that is saying that we have the magnitude of the force times the magnitude of the displacement times the cosine of the angle between cosine of theta, where theta is the angle between the force vector and the displacement vector. So let's say here theta equals angle between F and X. So really what we're looking at then, if you decompose the force vector into horizontal and vertical components, we have a parallel component and we have a perpendicular component. So the perpendicular component is equal to F sine theta, and the parallel component is F cosine theta. Okay, so we can say then that our work done is equal to F x cosine theta, or F cosine theta times x. Okay, and another way of writing that then is the parallel component of the force multiplied by the distance. So that's really what we mean here, is we mean that it's the part of the force that's parallel to the displacement vector multiplied by the displacement. And so if it turned out, for example, that the angle were 0, then it would be just simply force through a distance. And so that would be the case here with this mass. If I pull on the mass in the same direction as the displacement, the force and the displacement vector, as long as I don't tip it over, are moving in the same direction. However, if I were to pull like this, then only the part of the force that's acting in the direction of the displacement would contribute to the work that's done. And if I were pulling like this and the thing were already sliding, then the force would do no work at all. Okay, so this vertical force would do no work. I would have to do the work by pushing against gravity pushing against the friction force with my finger. Okay, and so in that case it would be F cosine 90. So there'd be no parallel component of the force in the direction of the displacement. All right, so that's what we mean, and we'll get into other versions of the dot product a little later on that That's essentially what we're looking at here with the work. And so that's true then. This simple version of the work expression is true if and only if the force is constant over that distance. If it's a non-constant force, then we have an integration expression that we'll need to look at later. But for the moment, we'll assume that our forces have a component that's in the direction of the displacement. And so let's go back to this problem, and let's say that the force is 100 newtons, and that the angle is 30 degrees, and that we pull this mass a distance of 10 meters. Okay, and let's not worry about any other forces for the moment, although we do have a normal force and we have mg. We won't need to worry about those yet unless there is friction. And so let's just find the work done by our force F. Okay, so there can be work done by different forces. There could also be the work done by friction. Would there be work done by the normal force? Well, no, because the normal force is perpendicular to the direction of motion. And so the normal force would do no work because it's has a 90-degree orientation with respect to the angle. But the work done by F would be here F cosine theta times x, or that would be 100 newtons times the cosine of 30 degrees. Which is root 3 over 2, which gives us 80, and then we have to multiply that before we go any further by the displacement vector. And so the displacement vector here is 10 meters. So that'll give us 1,000 times root 3 over 2, which is 866, and the units for that are Newton meter. Okay, now it turns out that because we don't like having to use combinations of units if they're often used in a problem, we have an abbreviation for Newton meters, and we call it a joule. This is also a unit of energy, as we'll see later. And by definition, that's a Newton meter. And so we can write this then as 866 joules. And so that's how much work I've done in the process by my force, which is oriented at a 30-degree angle in order to pull this mass across the surface. Now, one thing that we would want to make sure about here is that the mass itself is enough so that the normal force doesn't go negative. Because if the F sine theta component of the force is greater than mg, then what would happen here is that this thing would go right off the table. I'd pull it right off the table because I'd be pulling too hard. It would lift it as well as move it in the horizontal direction. Then I'd be doing work in the vertical direction and in the horizontal direction. But in this problem, let's assume that the mass is 10 kilograms. Okay, so that we could then work out what the normal force is, and then if we had a coefficient of kinetic friction, let's say that now we'll make this problem a little more complicated by saying mu k is 0.5 and the mass is 10 kilograms. Then the sum of our y forces is going to be equal to F normal plus F sine 30 minus mg, and that'll equal 0. So this gives us an expression for the normal force. Why do we need that? Because we might also want to find the work done by friction. Okay, so, and this is a more realistic problem then, one in which as I pull this thing along the surface, not only do we have the find a slippery part of the table. There we go. Not only do we have the there. Not only do we have the force applied to the right, which has the F cosine theta component, but we also have the friction force. And this is actually generating a torque, which is tipping this over, which is something that we'll talk about later. For the moment, we'll assume that the mass is small enough so that that effect doesn't really happen. But we can see that it does happen, and so when we get to torque, we'll learn more about how to deal with that tipping over problem. So here, the normal force is equal to mg minus F sine theta. And so this is actually a problem that we solved before. This gives us m is 10 kilograms times g, which is 10 meters per second squared, minus 100 times the sine of 30. Sine of 30 is 1/2, so that's 100 minus 50 equals 50 newtons. So our normal force is half the weight because of the F sine theta component lightening the load. mg is bigger than F normal because F sine of theta can help in this process of lifting and lightening the load so that the surface doesn't have to exert as large of a normal force. So if we want the work done by friction, that's going to be equal to the force, which is the coefficient of kinetic friction times the normal force, times the displacement, times the cosine of 180 degrees. Why 180? Well, because the force of friction is acting in this direction, force of kinetic friction. And the direction of motion, though, is this direction. So clearly then the angle between the displacement vector and the friction force is 180 degrees. And so this gives us a negative force of friction through a distance. Or this is equal to 0.5 for the coefficient of kinetic friction times the normal force, which is 50 newtons, times x, which is 10 meters, assuming that this thing is still moving through a 10-meter displacement while friction and this applied force are acting, times -1. All right, so that gives us 500 times 0.5 is 250 joules, but with a negative sign out in front. Okay, so the work done by friction is negative, and what that's telling us is that the system left to itself is going to lose energy. You slide it along and it comes to rest because of friction. And so even though I pull on this, and that causes a little bit less friction to act, because that means there's a little bit less normal force, there's still a negative force of friction that's slowing it down, and we have a force that's speeding it up. Okay? And so the one that's slowing it down is, we'll see, that's equivalent to doing negative work. It's the same thing as stealing energy from the system. Energy is leaking out of the system with a negative work done. And so therefore we could find the total work done, work total, and work is just a scalar. Even though we're multiplying vectors, we're saying here work is F dot x. The dot product of two vectors is a scalar quantity, which means we just add the individual works together. We don't take the component of a work vector because it's not a vector. Even though it's composed by the multiplication of two vectors, it's a scalar in itself. So this would be the work done by the force, which is acting, plus the work done by kinetic friction. And so that's going to be 866 joules minus 250 joules. And so that would give us 616 joules for the total amount of work that's done. Okay, so in each case, when we're looking at the work done by the friction force and also the work done by the external force, we are dealing with constant forces that are acting. And so that we can use this F dot x to get the work done. Okay, and so that gives us the total work. But the question then is, well, how is this useful? How can this help us solve problems, say, that we didn't know how to solve before? Well, let's say here that there's an initial velocity for this mass. So let's say that V naught here is equal to 2 meters per second, and we want to know what V final is. We'll say V final equals cross number. How can we do that by knowing how much work is done? Well, what we're going to need to do here is introduce the concept of energy. And so a certain amount of work then can be associated with a certain change in energy. Let's see how that would work. We say F parallel times x, and in this problem, let's just assume that the angle is 0 degrees, just for simplicity. Then, if this is the case, then we can write F as mass times acceleration times x. Okay? But using a kinematics equation for a constant force, we can say that V final squared equals V initial squared plus 2ax. Okay? And so our work done then is equal to max, and so then here ax is equal to V final squared minus V initial squared divided by 2. Okay, so then this is going to be equal to m times V final squared minus V initial squared over 2, or that's equal to 1/2 m V final squared minus 1/2 m V initial squared. Okay, so the work done then is the change in something, and so let's just for fun define this something to be kinetic energy. So if we define this energy, which is the difference between 1/2 mv squared, as kinetic energy, then the work that's done is equal to the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. And so you might say, well, now I want to find V final. That's the question here. If we want to find V final, then we already have the work that's done, because we have the work done by the external force and the work done by friction already figured out. We can just set that equal to the difference in 1/2 mv squared and then solve for V final. That's our only unknown. So you might say, well, we could already have done that, because before we learned Newton's second law, so we get F equals ma, and then once we have the acceleration, we can use this as a kinematics problem to find v final. And so that would be correct. You could do it that way too. But the advantage of doing this with the work energy principle is that even though so far we've been looking at work energy in terms of a constant force that's acting, it'll also act for a variable force too. And so variable force, we can't just use our kinematics equations, but we can still use the work energy principle. So I'm going to introduce the work energy principle with constant forces, but then we'll look at some variable forces, which is the real power of being able to use work and energy to solve a problem like this. All right, so we already have this value for the work that we got from two previous calculations that we've done. Great thing about looking at this on video is you can always go back, double check those things, make sure you've taken good notes on that. But now let's find v final from this expression. So that gives us 616 for the work that's done, joules, equals 1/2 m, that's 10 kilograms, times v final squared, minus 1/2 times 10 kilograms times v initial squared. And we were given over here that v initial was equal to 2 meters per second. So this would be 2 meters per second quantity squared. Okay, so I'll crunch this down to a number now. 616 equals 5 v final squared minus, this is 5 times 4 is 20. Right? 2 squared is 4 times 5 is 20. And so then we'll add that to both sides, and that gives us 5 v final squared equals 636, or v final equals square root of 636 divided by 5. So it's a pretty straightforward process then of solving for the velocity. And that gives us 11.2 meters per second. Okay, so we just solved this problem using the idea of work and then setting that work equal to the change in kinetic energy. Work equals delta KE. Okay, but you might be asking, okay, well, what about a really useful application where it would be hard to use our constant acceleration kinematics equations to develop an expression for the work done is equal to change in kinetic energy? What if we have a variable force, in other words? Let's try a problem like that. This is a more general expression for the work. And what we need here is a force as a function of displacement. So the force will not be a function of time, but rather will be a function of where we are. So for example, here, we could say this is x equals 0, and we could say that our force is equal to 3 plus 2x, where as we go through greater and greater x displacements, say here this is x equals 5, the force here would be 3 plus 2 times 0, or 3 newtons. The force here would be 3 plus 2 times 5, or 13 newtons. So the force then is increasing with x. Okay? And so you say, well, I'm kind of used to the force increasing as a function of time. And so why are we doing this in terms of x? Well, a lot of forces are distance dependent. And spring forces, for example, which we'll get to very soon, are spring dependent. So that's a function of where the spring is, how much it's stretched, rather than how much time has elapsed. So if we have this as a function of displacement and not a function of time, then we use the work energy expression. If the force is a function of time, then it turns out we're going to use the impulse momentum expression, which is in a future chapter. And we'll get to that later. But here we're just dealing with variable forces that are a function of displacement. Now, if you had something that was a function of time, could you turn it into something that's a function of displacement? The answer is yes, but it's not always the easiest thing to do. You need parametric equations that relate the displacement to the time, and then you'd have to reformulate your force to get it that way. But here, let's just say this is what we got. And so at some general position x, this force is just going to be 3 plus 2x. And this is acting in the direction of motion. So for a problem like this, the work done would be equal to the integral of f dot dx. And so what is that? Well, this is the same thing. If theta is 0, this is just the integral of f dx times the cosine of 0. If, and only if, theta is equal to 0. But let's look at that. Or we could also equivalently be looking at the parallel component of the force in the direction of the displacement. So the work done would be a definite integral then. In this case, let's find the work done in, if the force acts from x equals 0 to x equals 1. So how would that look on a graph? Well, when we integrate something, we're finding the area under a curve. And so that's a basic property of the antiderivative. So in this case, the work done would be the area under the force versus displacement curve. So at x equals 0, f is 3, and the slope of this line is 2. 3 plus 2x. So the vertical intercept, the f-intercept at x equals 0 is 3, and then we have a slope of 2. And so if I want the work that's done, basically what I'm doing is I'm saying, well, this little area here is f dx. That's a little tiny bit of work that's done. And so the height then would be whatever the force is at that point times that little bit of displacement. And so when you're adding up all the little dw's, the integral of dw is just summing up all those little rectangles from 0 to x of f dx. And that's equal to w. That's our total work that's done. And that's the change in kinetic energy. And now how can we show that that's true? Well, we know that work is equal to the integral of f dx. And we can write f as m dv dt times dx. And then we can use a chain rule to write this as m dv dx times dx dt times dx. And then I can cancel out the dx's here. And this gives me mv dv, integrated from v naught to v final. Right, so that's going to be 1/2 mv final squared minus 1/2 mv initial squared. So you can see that even with a variable force that's a function of displacement, we still get the same expression for the work as being the change in kinetic energy. And what this shows is that this work expression is going to be valid even if the force varies but the only way we can integrate this is if the force is as a function of x, because our integration variable is x. Right? So if it's a function of t, then we'd have to turn it into a function of x before we could even do the integral. All right? So you'll be given the force as a function of x in these kind of problems. But this shows that the work done even in a variable force problem like this is still the change in kinetic energy. And so this problem then is equivalent to finding the area under this rectangle and setting that area equal to the change in kinetic energy. So let's assume here in this problem that the initial velocity v naught is equal to 1 meter per second, and we want to find v final at x equals 1. Okay, so that's what we're looking at here. We'll find the work if the force acts from x0 to x1, and then if v naught at x equals 0 is 1 meter per second, let's find v final at x equals 1. Okay, so first we'll find the work, then we'll set that equal to the change in kinetic energy and solve for the final velocity. Analogous to what we did before, but in this case with a variable force. Okay, so the area under this curve, we could do it that way if we wanted to. Then this would be 0, 1. This would be 3. So the area is going to be 3 times 1 plus 1/2 base times the height. Okay, so this is x equals 1. Then the force is going to be 3 plus 2 times 1 is 5. Okay, so we'd have 1/2 the base. The base here is 1 times the height, going from 3 to 5, that's 2. So that gives us an area of 3 plus 1 is 4. Okay, and so I'm just doing that to show that if I do this integral now, I'm going to get the same thing. And sometimes you might want to do it this way. Instead of setting up the integral, you can just find the area under this curve. And in particular, when we get to thermodynamic problems, several of the problems are more easily solved just by finding the area under the curve. But here we want to stay in good habits of actually performing the integral, because if this weren't a straight line plot, then we would have to figure out what the area under a curved plot is, and that becomes much more difficult to do. All right, so our work done then is the integral from 0 to 1 of 3 plus 2x dx. And so that's going to be 3x plus 2x squared over 2, which is just 3x plus x squared from 0 to 1. That's going to be 3 times 1 plus 1 squared, which is 4. And so that would be 4 joules. And that's exactly what we got here, just using our little geometric thing to get there, 4. And so that's a quick little check. And it also helps to solidify, hopefully in our minds, the fact that when we do this antiderivative, this integration procedure, that we are in fact taking the area under this curve. And so that 4 then, that 4 joules for the work is equal to 1/2 mv final squared minus 1/2 mv initial squared. And so if again we're solving now for the final velocity, we can say, following through the algebra here, that v final is equal to 2w over m plus v initial squared. Okay, just solving this for v final squared, I'm taking both sides of the equation, I'm multiplying that through by 2 over m, both sides. So this gives me 2w over m, and here that just isolates the v initial squared. So v final squared then is going to be 2 times w, which we got was 4 joules, divided by m. So let's say that in this problem our mass is 2 kilograms. We have 4 joules divided, 2 times 4 joules divided by 2 kilograms plus 1 meter per second squared. So that'll give me 2, the 2's cancel, and so we're just left with 4 plus 1 is 5 for v final squared, or v final is equal to the square root of 5 meters per second. Which is 2.23 meters per second. Okay, so we did a similar process to what we had done in that other example with pulling the mass along at an angle with friction. But here we used a distance-dependent force. We integrated that variable force, got the area under the curve, and then set that equal to the change in kinetic energy to get the final velocity.